Welcome to Algebra 2. Today we've got section 10.5, combinations and permutations. Now, we've been spending quite a bit of time talking about probability of events occurring, and so far our options have been pretty easy to calculate as far as, what is the size of our sample space? Those numbers have been pretty easy to work with, but as you can imagine, if we were to look at experiments that were covered on a much grander scale, we might not always be able to use the tactics we have thus far. Now, just going to give you a little bit of a warning. This lesson is going to be a long one. You might be able to see over there in the little gray bar, we've got 18 slides, which is pretty long for a lesson here in this class. But there's a lot of different topics, and the problems go pretty quickly. Just be aware that we are going to devote 3 days of class time to this section at least, because we want to get the terminology down and understand what the questions are asking us. That's kind of been a running theme of ours throughout Chapter 10. It's that it's the vocabulary that's difficult, not the math. So let's get started. First, some of this terminology. The main thing that we're trying to figure out, like I said, is a larger sample space. So for a lot of the questions, they're going to be asking how many ways. This is not a probability question anymore. So we're kind of sidestepping that for a second to just ask how many ways could a certain event happen. So far we've talked about the grinded out method where we list the whole sample space and kind of think through all the different coin flips or dice rolls or marble draws or anything. And that's worked decently for us so far. We've had pretty manageable sample spaces. We've also had the menu problem. That's also called the fundamental counting principle, where we would multiply our choices. Those are the two processes we've really used thus far to calculate our sample space. But what if there are other conditions? What if the order matters when we're drawing objects? We haven't come across that just yet. Maybe a little bit with our conditional probability. But what if we have a selection of objects and we're only choosing a certain number out of them? That greatly increases our sample space, the size of that. So there has to be a way to fast track that. And one way to do that is through the use of what we call in math a factorial number. Now you may have heard of this, but it is, if I want the factorial of a number, I take the product of that integer and then all positive integers below it. And it's shown with an exclamation point. So you can see down below, if I wanted to take n factorial, I would take n times one number less times another number less all the way until I get down to times 1 at the very end. Okay, so in certain cases you will come across a 0 factorial, and by definition 0 factorial is equal to 1. That completes our definition for a factorial, so we must have that little disclaimer there. All right, so maybe just as a quick sample off to the side, we would show that, because with variables it's kind of tough to see. If I wanted to do 5 factorial, well, that's equal to 5 times 4 times 3 times 2 times, and we end up at 1. So it ends up equaling 120. So a factorial of a number is just a much larger number. All right, now the section title, combinations and permutations. We've already discussed that we're trying to answer the how many ways question with this. A permutation is a case where order matters. So we'll see words like arrange, the order matter, how we're finishing a race is another good way, because if we have 12 participants in a race, then 12 different people at the start of the race could possibly win. After that person crosses the line, then there's only 11 left. That person crosses the line. Then for third place, we've only got 10 contestants left. So the order that we choose these finishers does matter. Okay, so using that race as an example, you can see the first formula. If I have n objects and I'm going to arrange all n of them, then that is n factorial. Because if we think of our race example, if we have 4 people competing in the race and we want to find out how many ways all 4 of them could finish, we have 4 choices for first place. After that person crosses the line, there are only 3 people left running, so 3 options for second place. And then after that person crosses, then there are only 2 people contending for third place. And then finally, there's only 1 person left running that could possibly take fourth place. But again, maybe we're not going to look at this whole field of four runners. Maybe we're just going to say, well, how many different ways could they finish first and second? Well, then we have to adjust our formula a little bit. It's still running on factorials. This is the one that works every time, so this is the one that is worth remembering. So we have n objects, and we are going to arrange r of them. Okay, so how that adjusts our formula, if we look over here in the example, let's say there are four runners in our race, and we want to find out how many ways they could finish first or second. So I'm just going to arrange two of those four. Well, in the numerator goes the factorial of all of our number of objects. And then in the denominator, we want to divide out what's left after we take out those two. So we do 4 minus 2 factorial. And you can see what happens in our formula. We still have our first and second place finisher, but the third and fourth place that we don't care about, those have been canceled out by the denominator. Okay, so there is the math for it. The calculator can also handle this very well. To get to this NPR thing, n objects, we're going to arrange r of them. It's the following keystrokes. You hit the math key, and then it's PRB. It may also say prob for probability, and then NPR is an option. Okay, but what if we don't want order to matter? Well, that's called a combination. And instead of arrange, we use the verb choose to describe a combination. So this, instead of finishing a race, if we have, if I'm looking out at a classroom of students and I just want to choose 3 of you to be on a committee, the order that I choose you doesn't matter. It's just how many ways can I grab 3 people to be on that committee. So committee is a good way to think of combination. All right, so our formula, you'll see that we have n objects, we're going to choose r of them, and it's still driven by factorials, except now not only are we dividing out the remainder, how many people are left over, but we're also in the denominator dividing out the ways to arrange those objects. So the formula does make sense because not only are we choosing our objects, but we're dividing out the ways that we could arrange them. So the arrangement clearly doesn't matter here. Calculator again can handle this using that probability menu. And finally, for our processes here, I know it's kind of turning into a long lesson already. Pascal's triangle, we saw this in chapter 4 when we were expanding a binomial raised to a power. And you remember that what that did was it set up a combining of like terms. It makes sense. It's a combination. It combines things. So this actually ties in really nicely into our combination process. And this slide right here will really lead us into section 10.6 very nicely. But just kind of showing this together, this Pascal's triangle, this brilliant pattern that we have. Remember, we started off with the 0th row because it was possible to raise things to a 0th power. And then remember how we generated the pattern. We start off with a triangle of ones, and then to get each number, we would sum up the numbers up above it. So we could generate Pascal's triangle very, very quickly. Well, now to translate that into this combination concept, what we're thinking is it's row, choose, term. So instead of n objects, I'm choosing r of them. Say I want that row, choose that term in the row. Okay, so if looking at the triangle here, you can see they've done a nice job here. I like the way the textbook has set this up. They show it expressed as a combination as well. So if we wanted to calculate 3, choose 1, we go 0th, 1st, 2nd, 3rd row, choose the 0 first term. So very quick way, if our combination is something that has small numbers, Pascal's triangle can take care of a lot of that math for us. Okay, and then we can adjust how we expanded a binomial by looking at this binomial theorem down below. And again, this is what we will explore a lot more in section 10.6. But what it's saying is that each term can be found by using that combination for a coefficient. Then the first term raised to a power that is objects minus choices power times the second element of our binomial raised to that bottom number power, or whatever we are choosing power. This makes it very fast to expand, especially when we have the calculator at our side as well. Okay, now let's get into some examples and put all this to practice. I know we've got a lot of information that we've covered here. I'd encourage you, if at any point you wonder where I'm getting these numbers or where these processes are coming from, go back and look in your note packet or in this video even to the earlier slides to tie that together. We want to connect that knowledge with what we've already covered so far. So for number 6, in this first example, our directions say find the number of ways to arrange all of the letters and just 2 of the letters in the given word. So for number 6, part A, water, I've got 5 letters there. I see the word arrange in the instructions, so of those 5 letters, I want to arrange all 5 of them. Okay, and remember, we see that word arrange, we should be thinking, okay, NPR, lowercase r, that's n factorial over n minus r factorial. So for this first one, remember the number out in front is the n, how many objects. After the p comes the r, how many I'm choosing, or how many I'm arranging in this case. So I've got 5 objects, and that goes over 5 minus, I'm choosing 5 of them, or I'm arranging 5 of them, that factorial. So it's 5 factorial over 0 factorial, and we said by definition, 0 factorial is 1. So my answer is just 5 factorial, and we can calculate that out. The factorial key is also in that math PRB or prob menu if you wanted to insert an exclamation point. So that's 120 ways to arrange all 5 of those letters. And then part B, what if we only want to arrange 2 of them? Well, I've got 5 letters in the word. I want to arrange 2 of them. So in the formula, that's 5 factorial over 5 minus 2 factorial. That's 5 factorial over 3 factorial. Okay, and now simplifying it, factorial is a repeated multiplication, and then I'm dividing away. So there should be a case where the division undoes some of the multiplication that's happening. So let's just express this. These numbers are pretty manageable. I've got 5 times 4 times 3 times 2 times 1. And in the denominator, I've got 3 times 2 times 1. Oh yeah, so I do have a lot of division occurring that's undoing the multiplication by the factorial. The answer is just 5 times 4, 20. All right? And again, I've adjusted the instructions from the homework assignment. I want you to practice using this factorial. Because it simplifies so much, it's a good opportunity for us to brush up on some number skills. But the calculator is a great way to check with this. I really want us to get used to simplifying these. Flowers, I've got 7 letters. How many ways can I arrange all 7? Well, that's 7 factorial over, I'm going to have 7 minus 7, that's 0 factorial in the denominator. So that is just 7 factorial, and we could use a calculator or multiply it all out. What we get is 5,040. But again, I would be writing this out, familiarizing myself with the factorial definition for a permutation. Letter B, what if I only want to arrange 2 of those letters? Well, I've got 7 letters to choose from. I want to arrange 2 of them. Okay, well, here that's 7 factorial over 5 factorial. And if I think about the expansion, I've got 7 times 6 times 5 times 4 times 3 times 2 times 1. So I've got 7 times 6 times 5 factorial all over 5 factorial. So we get that cancellation to happen, and I could just write the factorial there because I no longer need to write out all those numbers counting down to 1, my answer is 42. Okay, straightforward enough. I can't stress enough, though, how important it is to write out good examples where you're showing your steps. Show what formula we started with because it said arrange. Show where all the numbers are going. This is going to make it easy to use your notes in the future when they're most needed. All right, second example, evaluate using factorials. Here's where I adjusted the instructions. I was off by an example. Then we want to check it with a calculator as well. So here, 6p5. So we're talking arrangement here. So same formula that we used on the last slide. I've got 6 objects, and I'm arranging 5 of them. So 6 minus 5 factorial is my denominator. That's 6 factorial over 1 factorial, which is just 6 factorial. So we think, okay, 6 times 5 times 4 times 3 times 2 times 1. Well, we already covered that 5 factorial is 120. So if we wanted to do that in our heads, we could say, oh, I'm taking that 5 factorial, but I'm bumping it up 1, so I'm multiplying in the next number up. I'm multiplying in a 6. We get 720. But again, see how that formula works. See how to simplify those factorials. Our third example here, 6 friends go to a movie theater, and how many different ways can they sit together in a row of 6 empty seats? Okay, so I'm going to show you 2 different processes here. You could think in a formulaic way, like I've seen in the past 2 slides. We could say, okay, there are 6 friends. We're going to arrange all 6 of them. That's one way to think about it. So that would mean 6 factorial over 6 minus 6 factorial. Oh, we just found 6 factorial at 720. Or you might think of it more visually. Maybe you think, okay, here are the 6 seats. And you may think of it more of like a finishing a race problem. So we've got these 6 friends that are going down the aisle to get to their row of seats. The first seat in the row, any of those 6 friends could sit down. They sit down in the seat. After that person is seated, now there are 5 friends that are jockeying for that next seat in the row. That person sits down, and there are 4 friends that could sit in the third seat. They sit down, and there are 3 friends left for that seat. They sit down, then there are 2 more friends for that seat, and then finally the last friend is stuck with the last seat. But notice what we had just written out here, 6 times 5 times 4 times 3 times 2 times 1, that is 6 factorial. So we do get the same answer. It's just a different way of thinking through the problem. Both about the same amount of, I don't know, mathematical knowledge required, but, sometimes it's just the way you think about it. What makes sense for you? All right, so up until now, all of our examples have been how many ways, right? All of our word situations have been how many ways can a certain event happen. Well, now here in number 20, we make 6 posters to hold up at a basketball game. Each poster has a letter of the word Tigers written on it, and you and 5 friends are going to sit next to each other in a row. The posters are handed out at random. Find the probability that the Tigers is spelled correctly when you hold up the posters. So probability, now we're thinking it's got to be between 0 and 1. Now we're looking for a fraction or a decimal or a percent or something like that. We don't want to just hold up those posters and have it say Gristy like you see right there. Well, okay. How many arrangements are the correct one? What is our desired outcome? How many ways could I get that desired outcome? There is one way. Tigers. There's one way that we could hold up those posters and have it spell Tigers. Now, what is our sample space? Well, that is the arrangement of all 6 of those posters. So 6, arrange all 6 of them. So you can see our how many ways has become the sample space of this probability problem. And since we've already done 6p6 quite a bit, it's just going to be 6 factorial. We saw it in the last example with the friends sitting down in the movie theater. I know the probability is going to be 1 over 720 because I know that 6p6 is 720. But again, just a slight adjustment in how we're setting up the problem to answer not how many ways, but what is the probability. Okay, so moral of the story, make sure the posters are in the right order. Not very likely that they're going to show up correctly, chosen at random. All right, example 5. Our vocabulary has changed. Count the number of possible combinations of R letters chosen from the given list. So now it's a combination. Order does not matter anymore. So here in number 24, I've got 1, 2, 3, 4, 5 letters. And of those 5 letters, I'm just choosing 4 of them. The order that I choose them doesn't matter. So I'm not arranging them, I'm just grabbing them. Okay, well, good opportunity to practice that new formula that says if I have n objects and I'm choosing R of them, still starting out with the objects factorial, still dividing out the ones we are not choosing, but then we're also in the denominator dividing out the ways to arrange those objects we're choosing. That's how we account for the order not mattering. All right, so 5c4, that would be 5 factorial over 5 minus 4 factorial times 4 factorial. Again, just familiarizing ourselves with the formula here and getting extra practice simplifying factorials. All right, so what's this going to look like? Well, I've got 5 times 4 times 3 times 2 times 1 in the numerator. In the denominator, I've got 1 times 4 times 3 times 2 times 1. Just expanding out that multiplication. This is what we should be visualizing in our heads as we simplify factorials. Hopefully we get to that level. And you can see we've got a 4, 3, 2, and 1 that are multiplied into both numerator and denominator, so they cancel. There are 5 different ways to choose 4 letters. Well, Mr. Hartz, that seems like a really small number. If we got 5 letters and we're choosing 4 of them, why is that 5? Well, what I hope you can if you can see this, then you're really, really good. But if I'm trying to find out how many ways I could choose 4 of the letters, it's also the same as saying, well, how many ways could I leave one of those letters behind? So if I were to grab D, E, F, and G, I'm choosing 4, but I'm leaving the H behind. I could also grab D, E, F, H and leave the G behind. So really, the 5 possibilities are just, well, I could grab 4 letters, leaving one of those original ones behind each time. Cool concept. 34, you want to purchase vegetable dip for a party. A grocery store sells 7 different flavors. You have enough money to purchase 2 flavors. How many combinations of 2 flavors are possible? Okay, now don't read too far into this. You're not trying to mix 2 different ones together or anything like that. Any type of chemistry going on here. All you're doing is you imagine that you're looking at all these different containers of vegetable dip on the store shelf. How many different ways could you close your eyes and just dump 2 of those into your cart? So there are 7 different varieties. It doesn't matter what order they're in. I'm just going to choose 2 of them. How many different ways could I choose 2 of them? And again, let's practice our factorial definition of a combination. Okay, that's the same as 7 factorial over 5 factorial times 2 factorial. So I've got 7 times 6 times 5, 4, 3, 2, 1, and I know that immediately I don't have to expand it any further. I can just leave it as a factorial because it's gotten to a point where I can cancel out the 5 factorial in the denominator. So what I've got is 7 times 6 over 2 times 1, and the 6 and 2 can simplify to 3 over 1. My final answer should just be 21 different ways. And of course, it's not required that you do it this way. It's just sometimes if you can see that happening, it's a lot faster to cancel them in line than to try and do it in a calculator or anything like that. Factorials simplify pretty easily. Okay, next one. Tell whether the question can be answered using a permutation or a combination. Explain why you chose that one, then answer the question. I wish there were more questions like this in the actual homework assignment, just because that's one of the questions we have to ask ourselves. Which one are we going to use? NPR, NCR? Are we going to try and find a probability? You know, it's important. It decides the outcome of our problem, and they could be vastly different if order matters or doesn't matter. So 38, 10 students are auditioning for 3 different roles in a play. In how many different ways can the 3 roles be filled? Now, 3 different roles. So when we choose that first person, we're choosing them to be the lead role, right? We're not just choosing 3 of them to be stagehands where their roles are all the same. We're choosing them to have different responsibilities. Okay, so this means that the order we choose those auditioners matters. So I've got 10 students, and I want to arrange 3 of them into the first part, second part, and third part. It's like finishing a race. So, okay, before we do the math, that word different is telling us that we have to use a permutation because order matters here. So when we do our 10p3, we're simply doing that calculation, 10 factorial over 10 minus 3 factorial. Right? It's a permutation, not a combination, so we're back to that. The denominator will become 7 factorial, and if I expand out the numerator, 10 times 9 times 8 times 7 and the rest of the way down, that is 7 factorial. We find that our answer is just 10 times 9 times 8, 720. That's how many ways the roles can be filled. Notice they didn't say what's the probability, so I know that my answer can be greater than 1. That's totally fine. They're saying how many ways. Another key vocabulary concept. Next example, you work 5 evenings each week at a bookstore. Your supervisor assigns you 5 evenings at random. That's pretty cool, cruel boss, from the 7 possibilities. What is the probability? Okay, probability, I know my answer is going to be between 0 and 1, that your schedule does not include working on the weekend. Huh, okay. Well, think about what's happening, because our sample space and our desired outcomes are going to be determined by answering how many ways. So let's see, out of all the possibilities, there are 7 possible evenings. That boss is going to choose 5 of them. And again, the order doesn't matter. He might pick Friday and then pick a Tuesday or something like that. The order doesn't matter. He's just going to pick 5 of those dates. What is the probability? Okay, does not include working on the weekend. That means if our employer were to choose, he's choosing all 5 of those days out of the 5 weekdays. Okay, so ways he could choose all 5 working days as weekdays, over how many ways could he just choose 5 days for you to work that week. All right, so let's figure this one out. And this one might be a good one to use a calculator on. I'm not sure. I'm just going to do this one factorial, though. For the first one, 5 factorial over 5 minus 5 factorial. And the order does not matter, so multiplying by the arrangement there, we get 5 factorial over 1 times 5 factorial. Okay, so our numerator is just 1. Now let's do our 7c5. Okay, so 7 times 6 over 2 is what we're left with. That equals 21. So sadly for you as the employee, probability is pretty slim that you won't have to work on the weekend. 1/21 is our probability that we get that free weekend in our schedule. Okay, just did that one. Next example. Use the given value of n to find the coefficient x to the n in the binomial expansion. All right, so what we've got is we've got this huge binomial expansion, right? I'm going to have something x to the 9th plus something x to the 8th, something x to the 7th, so on, so on, so on. We want to find out what the coefficient will be on our term that has x to the 2nd. So we're going to have something x to the 2nd. We want to know what is that number. All right, now here is where our combinations come in very helpful, because remember, it's combining like terms as we go along. So the one thing I do not like about this is that when they say that n equals 2, that is not this n. So I kind of wish they would have chosen a different variable in the textbook, but I get it. I get it. It's just some number. This is actually our n. So we could say, let's call this k equals 2. All right, so how are we going to set this up? We've got the first thing in our binomial, the 3x. We've got the second thing in our binomial, the -1. I've got n here. Well, let's take a look. The binomial expansion says we're going to do NCR, and then our first thing to the n minus r power times our second thing to the r power. Okay, so what I want is I want this x to have a 2 on it, and I know it's starting as a 9. So in order to make that x end up with an exponent of 2, my r has to be 7. We said n was 9. To get our desired outcome, we want r to be 7. So here's what we're going to do. We're going to do 9c7, and then our first thing is 3x to the 9 minus 7 power. And then our second thing, -1, gets raised to the 7th power. All right, well, let's figure out what 9c7 is. 9 minus 7 is 2 factorial. So that's 9 times 8. Sevens cancel. We get 36. Okay, so 9c7 is 36, and we could use a calculator for that too. Don't feel like you had to do all this in your head. And then next, I've got 3x, all of it raised to the 2nd power. That would be 9x squared. And then -1 to an odd power is going to hold on to its negative sign. So if I multiply all those together, I get -324x squared. So our coefficient is just the number out front, -324. Now, there's a lot involved with this problem, but if we can navigate this, we're going to be in really good shape. Just realize that our n value is the power that our binomial is raised to from the beginning. So we know as soon as that problem comes up that in our NCR, the n is 9. Then we can work around that to fill in the rest of the pieces. Okay, and our final example on this marathon of a lesson. Consider a standard deck of 52 cards, and if you need to see what a deck of cards looks like, remember I've given you that information earlier in this chapter. We knew we were going to see quite a few card draws and things like that when we were talking about probability. The order in which cards are dealt for a hand does not matter. Now, this is a crucial thing when you're dealing with card hand problems, because it's so tempting to think, oh, the dealer has the full deck of cards, and then they hand out one card. Then there's only 51 left. Hand out another card. But remember, what you're doing, if you're taking 52 times 51 times 50, you're establishing order. You're doing that factorial, finishing a race thing. It doesn't matter, because the order that you get your cards is irrelevant. Once you get those 5 cards, that is your hand, and it doesn't matter what order they are when they're given to you. So the order does not matter. I'm glad they mentioned that specifically in the textbook. Okay, letter A says, how many 5-card hands have all face cards? Well, remember, a face card is a jack, queen, or king times the 4 suits. So there are 12 face cards in the deck. Okay, so what is the probability that if we have this whole deck of cards laid out in front of us and we just reach in and grab 5 cards at random, how many ways can I choose 5 of just those 12 face cards? It's just asking how many ways. So if we do 12 choose 5, we could use our factorial definition. And I'm just going to try and simplify this on the fly. Realize we could have this a long time ago with the calculator, but kind of like the challenge of doing them by hand. I noticed that in the denominator, I've got a 4 times 3, which is 12. And I've also got a 5 times 2, which is a 10. So I'm really just dealing with 11 times 9 times 8 all over 1, which is 792. So 792, if you used a calculator, that should be what you arrive at as well. 792 5-card hands that contain all face cards. And if you're playing poker, you're pretty excited to get all face cards in a hand. All right, now letter B says, what is the probability of being dealt this hand? So now it's not how many ways, it is what is the probability. So my how many ways for the desired outcome is the numerator, but then we need to think how many different 5-card hands are possible in total. Well, the sample space is enormous. 52 cards, how many ways could I just choose 5 of them? All right, so there's our probability, and again, we used this counting to set up an order not mattering, choosing 5 out of 52 cards. That is our total possible outcomes. That's the size of our sample space. And definitely going to use a calculator for this one. The result, you can see why this is such a good hand in poker, 0.000305. That's our probability. The calculator will not even convert that into a fraction. Not very likely at all. Okay, here's a look at your homework assignment. Yes, it's a long assignment, but remember we are, pacing ourselves over 3 days, making sure that we understand how to use factorials to calculate these, understand the vocabulary, how to navigate the questions, what they're asking us. When does order matter? When doesn't it matter? Are they asking us how many ways? Are they asking us what's the probability? So again, something we definitely want to slow down and make sure we understand well as we look at this assignment. They covered a lot in this one section. That does it for 10.5 here in Algebra 2.